Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is a very interesting reagent, that is Burgess reagent. Okay, these reagents structure is this one. Now this reagent is utilized for tertiary alcohol to alkene conversion under milder condition. Generally for tertiary alcohol to alkene conversion we use any mild or diluted acids, but it has some negative points. For example, this reaction proceeds through carbocation as intermediate, so this carbocation can undergo some rearrangement. So there is an issue of rearrangement. Second point, if your molecule have some acid sensitive functional group, so that may be another problem for this, and for that purpose this Burgess reagent is actually a selective mild alternate option. So let's before going to the details, see one MCQ. So what is the major product of this reaction? You can say this is an secondary alcohol. If you treat with concentrated sulfuric acid and heat it, what will be the product? 4 options are provided and one of them is the right answer, but I request you student, please pause the video, try by yourself, and whatever answer you get, please write in the comment box along with few words as explanation. And don't worry, at the end of this discussion we'll get the right answer with proper explanation. So let's go to our topic, this Burgess reagent and its introduction. Now this Burgess reagent is actually known as this N-methyl N-triethyl aminosulfonyl carbamate. Okay, it's a name. It's actually a mild and selective dehydrating agent, and it can be successfully utilized for the preparation of alkenes from alcohols. Means it's a type of dehydrating agent. Now, and interesting features of the reagent is that the dehydration is pyrolytic reaction which can be happen below 100 degree. Generally we have seen this pyrolytic reactions needs high temperature, but this reagent is very unique. That's why it could be achieved lesser temperature, and this reagent is highly soluble in most common organic solvent even though it's formulated as salts. Actually positive negative charge, different position. Now in this case this dehydration takes place through a variant of EI mechanism and syn-elimination. Remember, this is a very important thing, syn-elimination. I'll give some examples later on. Now first of all, how this reagent is actually prepared. This is student prepared by reaction of this isocyanate. So actually this is sulfonyl chloride derivative and this is isocyanate, and these isocyanate, if you look at this part, is actually a carbonyl derivative. Okay, so I can say that this is delta positive. So consequently what happens, this alcohol oxygen lone pair, which is actually delta negative or nucleophilic in nature, it attacks here. So first it attacks here, it's open up and it comes back and negative charge goes on nitrogen. Now if you look at this alcohol, after nucleophilic attack will have a positive charge and it will release that proton, and after this nucleophilic attack this nitrogen is going to have a negative charge. So the proton from this alcohol will be shifted to nitrogen, and this OMe part of the alcohol will be attached to this carbon. So this is actually a N-methyl chlorosulfonyl carbamate, and this part is chlorosulfonyl and this is a methyl ester, so that's why methyl chlorosulfonyl carbamate. Now so this is the first place, and second place, see this molecule, one side you have consumed, that is isocyanate, but still this sulfonyl chloride is there. It's an acid chloride type molecule, but it is not that much reactive. Now it can undergo reaction with this. You can say that triethylamine is doing nucleophilic attack. This triethylamine is significantly bulky reagent. Yes, I agree, and it is attacking to sulfur center, which is also significantly crowded. It's true, but see student, there is no alternate option. So under this reaction condition it happens, and you can see it's happened under pretty milder condition. The first reaction, if you look at, that is also room temperature 25 to 30 degree, and second reaction, that is also. Now in first reaction you may consider it is driven by this bulk factor, steric factor, and second thing, only one reactive center is left. Fine. Now in this way it produces this reagent which is known as Burgess reagent. Now you can think that, wow, it's true, nucleophilic attack happened, but why negative charge is here? That's the question. So actually if you look at these NH, student, let me clearly show it. So these NH this nitrogen is in between there are two sulfur oxygen double bond and one carbon oxygen double bond. So you may consider it's like an active methylene or 1,3-dicarbonyl type. And we know 1,3-dicarbonyl or active methylene compounds are significantly acidic. By the way, I have already discussed a dedicated lecture on this topic. You may visit. I shall provide the link in description box. So it's a dicarbonyl, so it could easily be abstracted. Not only that, in the reaction medium there may be excess amine too, so that can abstract. So one side of this amine became since it's a tertiary amine, 3-degree amine, so it will be as salt. Okay, so this nitrogen is carrying this positive charge. In another side of this nitrogen, because of these double stabilization of that conjugate acid, means N minus, it became as N minus reagent. So actually the positive charge is on both nitrogen but with different position, and stabilization is also different. So this is, and you can see here that proton, taken from here, is abstracted as ammonium and it is in the form of salt. So this is, student, the Burgess reagent. Now actually how this reagent is acting as for this alcohol dehydration, or more specifically say tertiary alcohols. So actually if you look at this reagent is also, student, it is a tertiary alcohol, tertiary carbon, because this consider carbon and third part is obviously carbon too. Now this alcohol again attacks this sulfur center through acyl nucleophilic substitution. So first it opens up, then it's come back, and later it leaves. Now question, why it leaves? Because if it leaves, this triethyl amine is actually leaving, so it is, student, a neutral molecule, it's relatively stable, so it will leave, and ultimately this will produce a sulfur ester, means the sulfonic acid ester you may consider. Now actually this triethyl amine is, student, doesn't remain in this form. Why? Because after this nucleophilic attack, the oxygen actually have a positive charge, so that's why it need to release the proton. So who can abstract this proton? These release triethylamine abstract that proton and convert it is triethyl ammonium salt. Now if you look at the charge separation, this is the positively charged, this triethyl ammonium salt, and only negative charge is on the nitrogen. Fine. So now a simple question you can ask, that if you look at this overall reaction, the reagent, this Burgess reagent, so it was the reagent. Now initially the sulfur center was attached to a nitrogen carrying a positive charge, means this nitrogen was not donating, so it was withdrawing some electron density from the sulfur. So that's why I can say that this sulfur was significantly electron deficient, or in more technical term I can say it was a relatively better electrophilic center. Fine. But when this sulfur got attached to oxygen, what do I mean by the statement? So everything was as it is, OMe, and this another site O. So this is carbon attached to this this is carbon. So let me show you, this is attached to hydrogen, etc. So when this is attached, this part is attached. So if you look at this side, student, so this sulfur also has this oxygen, so it can also donate its electron pair in this way, or you can expect that, sir, it can donate and it can open. So this sulfur center is not that much electron deficient, agree? So this nitrogen lone pair is not that much delocalized, it could not be that much delocalized into the sulfur center. So can I say here that after this ester formation, basicity of these nitrogen increases? Obviously yes. So that's the thing. And second, proper conformational orientation. What do I mean by the statement? Just count the number with respect to nitrogen. This is 1, this is sulfur center 2, this is oxygen 3, carbon 4, this is next carbon 5, and hydrogen 6. So through a 6-member ring and syn-elimination, student, I told at the beginning that this word will come through this 5-6 member ring and syn-elimination, and this way alkene is produced. You can see this is the alkene, obviously this is the other part. So this is the overall mechanism for alcohol dehydration. Now let's go some example. Selectivity for alkene preparation. Now sometime before I have explained that this is a syn-elimination, so you can expect that it will abstract this proton, it will come, it will go. So in this way it will produce this. Now if you look at little closely, this phenyl and this phenyl, they are anti, and these hydrogen and this deuterium is anti, so that's why is this trans derivative. Okay, now you can think that, sir, trans I understand, isn't it possible that CC rotation happened because it's sp3 this carbon bond is sp3 so CC rotation not possible? Let's consider what will happen. So let's rotate it 120 degree, then deuterium will replace the hydrogen. So you can expect, since they are isotope in nature, so just you can expect that their chemical reactivity will be almost similar. So this is the hydrogen and above is deuterium, okay, and rest part, the below part is almost same. So you can expect that, see, this top side is pH, bottom is hydrogen, and above side is OSO2, this is N minus CO2 Me. Now what is the problem here? See, this phenyl or phenyl, since it is a syn elimination, so during this elimination these two phenyl needs to come in a same plane, very closer, so they should have a severe steric repulsion. So that's why that this previous compound will give only this isomer. But if you want to get the another one, for example this deuterium elimination, so you need to take its enantiomer. Now what do I mean? You can see here only the position of hydrogen and deuterium change, everything is same. So I can say here it is nothing but single exchange, and we know that single exchange changes configuration. For example, if other one, just for example, other was R, then route will be S. So this is another isomer, stereoisomer. So single exchange changes configuration. So this is a completely different molecule compared to the past one. So in this case, since they are in syn periplanar, so it will be abstracted, it will go and it will leave. And by the way, still here this phenyl and this phenyl anti. So in this way we will get this product with no deuterium. So I guess you have understood. And if you look at the condition, benzene and 50 degree centigrade, so such kind of reaction is very useful, low temperature. So that is the beauty of this reagent. So let's go to another examples. Selectivity of alkene preparation. Now, so 60 degree centigrade, this one means this Burgess reagent. Now these alcohol will undergo. So now in this alcohol, next carbon, there is one hydrogen here and there is one hydrogen here. And remember student, this position is called bridgehead position, and this bridgehead position double bond formation not possible because of extreme ring strain. So only these proton will be eliminated, and at 60 degree centigrade it eliminates selectively and produces the product. Similarly, if you look at this cyclopropane ring containing alcohol, so at 30 degree, just imagine room temperature, it produces this alkene. Now we'll think that, sir, obviously it's true that there is one hydrogen, or more accurately if you want to know that, okay sir, there is one hydrogen and there is also one hydrogen, it's true. Why not the hydrogen attached to this cyclopentane ring is not eliminated? Just student, if it's eliminated, what will be the product? This is the product. Now see, this is the sp2 carbon, attached to double bond. Now this angle must be should be a 120 degree, because we know in case of sp3 angle is 120 degree, but because of this three member ring or cyclopropane ring, it will have a significant ring strain. So that's why it is not produced, this is produced. Although the general tendency of such elimination is to follow the Z-shape rule or Z-shape rule, which dictates us that more stable alkene will be the major product. So you can see the example number 5, where this is the alcohol. So two options possible, it could be eliminated from here, it could be eliminated from here, but here the blue hydrogen is predominantly, so this part I am talking, eliminated. and it produces this more substituted alkene 2.4 compared to this is 1 less substituted. So this ZZ product dominate. Okay. Similarly, in the next example number 6, you can see this OH got deprotonated along with these hydrogen. So you can see here. So this is the product, major product. So this clearly indicates that such elimination prefers to follow the ZZ rule, that is the more substituted alkene or more stabilized alkene is expected to be the major product if there is no exceptional condition. Now let's go to another type of example, amide to nitrile conversion. Now if you look at this example, this is amide at 25 degrees centigrade, it converted into nitrile. Previously we have studied, student, that if you take an amide, if you take P2O5 and heat it significant, then water eliminated, and in this way it produces nitrile. But this is the beauty of these Burgess reagent, that room temperature you can achieve it. How? First this amide undergo tautomerization. These lone pair push here and it goes, and one proton shift from this NH2 to go there. So this thing is called, student, this is amide and this is iminol. Why? First this part, if you look at, this is imine and this is all. So this is iminol, tautomerism. So now next this alcohol follows the same pathway for elimination. Now a simple question, that if you feel any difficulty that sir, I don't understand the mechanism, I suggest you, student, please go back and see the mechanism of alcohol dehydration again. Now what is the difference? In this case there is one hydrogen, so rest of the things are similar. So in this way you can see through a 6-member type ring, 1 2 3 4 5 and 6-member type ring. By the way, student, don't get confused about this negative charge. It may looks little closer to sulfur, but no, this is not on sulfur, this is on this nitrogen. Okay, this nitrogen, don't get confused. So through 6-member ring it produces this nitrile. So one double bond is getting converted, so this is a double bond is getting converted into triple bond. Not only that, similar example, if you look at, this is actually another amide. Through similar process of reaction, so 1.2 equivalent of this, 2 equivalent of this reagent require and 12 hour. Now you will say that's at 32%. Is it that much important? Student, look at this moiety. This is a penicillin derivative. For such biomolecules, such kind of selective conversion is important. Okay, so in this way this medicine could be prepared. Now another example is oxime to amide. Now if you look at oxime, so this is, student, oxime, and how you can prepare this oxime? You can prepare this by reaction with any aldehyde, for example this benzaldehyde plus hydroxylamine, and the reaction is termed as sheaf-based condensation or imine formation. Obviously along with oxygen, one molecule of water is produced. I have already discussed a dedicated lecture on this imine or sheaf-based formation. You may visit for better understanding. And not only that, these nitrogens are far more active because of these nitrogen lone pairs are far more reactive compared to traditional amine because of alpha effect. Now let's come back to our main topic. So this oxime is produced, and this oxime OH still reacts with this Burgess reagent. What do I mean? Similar way it attacks through acyl nucleophilic substitution type reaction, it leaves, and ultimately elimination happens. And by the way, in this case the path followed little different. In this case actually the phenyl group migrates, and by the way I have taken from one paper, I shall give the reference so you may visit, and it produces this amide. Now see reaction conditions. So first step, room temperature, second 90 degrees centigrade, 30 minutes, 75% yield. So that's selective reaction. So it's a backpan rearrangement done by using this reagent. So in conclusion, what you have learned today, that it's a mild and selective dehydrating agent, and it can be successfully utilized for the preparation of alkenes from alcohols. Now conjugated amide and ion are actually more stable due to delocalization. Actually it's like an 1,3-diamine derivative, that type of thing you can consider. So the negative charge is doubly stabilized, actually triply I should say, 2s double bond O. Now the dehydration could be achieved below 100 degrees centigrade. It's a very important, it's a mild reagent, and here the reagent is highly soluble in most common organic solvent including non-polar one, even though it's formulated as salt. Actually you may consider zwitterionic type, one side is negative, one side is positive, like that. Now it could be utilized for alcohol to alkene, amide to nitrile, oxime to amide, etc. conversion, which we have explained. So this is the complete overall discussion about this reagent. Now it's a reference. The reference is this Burgess reagent inorganic synthesis. This is published in 2000 journal, in this Indian journal. Now actually by Professor Deepak Ranjan Mal. Actually I is one of the student also in my M.Sc time, 2 years. Okay, so let's go to our question. Now if you look at this MCQ, what is the major product of this reaction? So this is a secondary alcohol. As I told, this is a secondary alcohol center. So in terms of concentrated sulfuric acid, what is the major product? So let's go to the mechanism. So in case of concentrated sulfuric acid, it's protonate the alcohol, it gives H+. So that H+ will protonate this alcohol because this lone pair, fine, it will produce protonated species. Now second step, this water will leave. Why? Because in this case the leaving group is water, it's a neutral leaving group, and that's why it is stable. So neutral leaving group. Now in this way it will produce a carbocation. Obviously I can say it's a secondary carbocation. Now carbocation can undergo rearrangement if the product is more stable. So what happens? From here these hydrogen migrates with its bond pair, means hydride migration. So in this way it produces this tertiary carbocation. Now there is in this case two chances. So this is a tertiary carbocation, is highly stable through, for example, plus I effect and hyperconjugation both, but I am not going details. Now there are two options. What are two options? First of all, this proton could be eliminated and it can result in these alkene, and second option is that here there is another one proton here also. This is also alpha proton. So these could also be eliminated. Okay, and it will go there, so it will produce these alkene. Now if you look at, compare this versus this, for example this is A versus B, so I can say that A is more stable because more substituted. Okay, so A is more stable, so in this way I can say this is the product. So in this case, what is the major product? Obviously C is the major product. Now if this question appear in your exam less than 30 seconds, how could you come to the right answer? Now simple thing, you need to keep few points. First of all, alcohol in presence of acid could be protonated, and after protonation in presence of heat it leaves and produce a carbocation which can undergo rearrangement to produce the more stable carbocation, and later on elimination will happen, and in this way more stable alkene or more substituted alkene will be the major product, like Sedzev rule. So this is the product. So this is the end of discussion. I thanks everyone for watching. If you really enjoy the content of my channel, then please help this channel to grow, and if possible please visit my two another channels. So thank you for watching. See you in my next video. Bye bye.